This is my first time making a YouTube video of this variety, so you'll have to excuse me if the narration is a little rambly and I don't really know what I'm doing. What I want to do is explain how thrust in outer space is analogous to gravity on Earth in many respects. So here I have a pretty basic example. What I have simulated here is a small sphere, well, small, it's 2 meters wide, about 6'7", large enough for most humans to stand inside. And on Earth, in a gravity field, it just kind of stays where it is. Let's make this a little more interesting. Let's say it has an initial velocity of 20 meters per second, and works out to about 45 miles an hour. In such a situation, such a ball would go up for a while, and because gravity is gravity, it would eventually get dragged back down. It looks like the ball is bouncing here. Really, it's just that I'm looping the animation indefinitely. We can make an adjustment to this to get an idea of how high the ball goes. The distance between the bottom of the ball and the floor is represented right here. So you have initially it goes up very quickly, but it slows down near the top, gets to a maximum height, drops down. It reaches its maximum height in approximately 2.4 seconds. Get that here. Maximum height of about 20.4 meters, which works out to about 67 feet. And after it has done that, it just kind of goes back down. And so the animation moves. This is how things work in Earth's gravity. If you want to understand how things work in zero gravity, you want to look at this. There's a separate simulation of the same ball, given the same initial velocity of about 45 miles an hour, exactly 20 meters per second. And you see it just kind of keeps going. Because there's no gravity to slow it down, it just goes on forever. Let's add to this something so that you can maybe understand how a sense of gravity can exist in outer space. I'm going to add an artificial floor here, and I'm going to give it the exact opposite acceleration that an object on Earth would have thanks to gravity. That is to say, it is going to accelerate upward at 1g. This creates a situation where at first the ball and the floor separate, since the floor has a velocity of 0, but eventually the floor catches up. And what you find, if you try to work out the distance between the artificial floor and the ball, the distance looks very, very similar to what we saw in the first situation with gravity. In fact, the maximum height is exactly the same in both cases. Might be skipping frames here. I hope that isn't screwing up the simulation, but you should be able to see how this works. So if we look at 2.4 seconds, we find it reaches a maximum height of 20.4 meters. Again, that's about 67 feet. And then eventually the floor catches up because it's always speeding up and the ball is not speeding up, it's just keeping the same velocity. Eventually the floor will always catch up. Now let's have an idea of, let's look at the actual math here. I realize that the internet is generally allergic to math, but I think we can see a little bit of what's going on and why this is if we look at the equations involved. In the case of gravity, the height of the ball is given by this equation over here. This is the general equation for how to calculate something's position in a situation with uniform gravity. It's the initial velocity times the number of seconds, plus the acceleration due to gravity, which here is negative because it's dragging things down, times the square of the number of seconds, all that divided by 2. The specifics don't matter, just understand that this is the position of the ball. Now, to work out the difference between the height of the ball and the height of the floor, we need to subtract from this the height of the floor, which is 0. The floor doesn't move in our first example. So that gives us the equation for the distance between the ball and the floor in the case of gravity. Now let's look at the situation of thrust. The height of the ball is given by the equation the initial velocity times the number of seconds. You then subtract from that the height of the floor, which is given by this equation right here. Now I don't know if it's immediately obvious that these are the same equations. A minus and another minus are the same as a plus. And if you subtract nothing from something, you just get that something. Subtracting nothing is the same as not subtracting. and you find the two equations are the same. In the same way that these two equations are the same, a whole lot of other equations in physics are also the same between these two scenarios, between gravity and thrust. And that is how gravity works on a spaceship in the expanse. If the engines are on, the ship experiences artificial gravity because it's accelerating. If the engines are not on, the ship does not experience gravity because it's not accelerating. Technically, it's not really gravity. It's the illusion of gravity. But people in the expanse refer to it as thrust gravity, and it kind of makes sense that people would call it that. That's it. I don't really know how to end this video.